Hey everybody, this video lesson is going to take us through the difference between bond polarity and molecular polarity. When discussing the polarity of the molecule, it's important to determine whether or not someone is referring to the polarity of the bonds individually or the polarity of the entire molecule altogether. So what's the difference? I'm going to take you through that here. So buckle up, here we go. Bond polarity is measured using electronegativity values. It's a quantitative value, and in order to calculate the bond polarity, you need to take the electronegativities of the two elements and subtract them. Let's take, for example, the molecule you see in green, CF4. As you can see, it's made up of 4 equivalent CF bonds, so I'm going to circle one of them. Now the bond polarities depend on the electronegativity, and all you do is you find the electronegativity of the two elements and subtract them, similar to what we discussed in an earlier chapter. When calculating bond polarity, it's always important to take the bigger number minus the smaller number, or if you do the smaller minus the bigger, just take the absolute value of the number. It should always be a positive quantitative value. Since fluorine is the most electronegative atom on the periodic table, I'm going to make that En1 and carbon is En2. Now, I look up on the periodic table of electronegativity values and I find that fluorine has a 4.0 and carbon is a 2.6. After subtracting those two values, I get an electronegativity difference of 1.4. which is the bond polarity value. Even though there are 4 CF bonds, the bond polarity remains 1.4 because we're just trying to identify the bond polarity of one of the unique CF bonds. You don't need to multiply it by 4, add 4 together or anything. This is the bond polarity. Now there's something that we need to talk about that we didn't talk about in a previous chapter, and it's how to label the bond dipole. The bond itself is polar, and we need to label the positive end and the negative end of the bond. There's 2 ways to do this, but the way that I prefer is using an arrow. Now the arrow is going to start on one atom and stretch to another atom, and it's going to point towards the more electronegative element. In this case, it's the fluorine. So again, the arrow points towards the more electronegative side of the bond. Now the back end, or the tail, is crossed off with a plus sign to show the positive end. This labels the polarity of the bond, saying that the polarity of the bond favors the fluorine because that's where the most polar, the most electronegativity is. And the side that's opposite of the arrow is more positive. So if you're ever asked to label the dipole, what I mean is I need you to draw an arrow to represent the pull of the electrons towards the more electronegative atom. The word dipole refers to 2 parts of the pole. You've got the more electronegative side and the less electronegative side, or dipole. Molecular polarity, on the other hand, depends on the shape of the molecule. Now we're talking about the Vesper shape, the 5 shapes of the Vesper theory: the linear, trigonal, planar, trigonal, pyramidal, tetrahedral, and bent. It primarily depends on the shape, but if the shape is one thing, you also got to check the bond dipoles, which we discussed on the last slide. I'll take you through the steps on how to determine the molecular polarity of an entire molecule. Sometimes molecular polarity is also referred to as the overall polarity. Unlike bond polarity, molecular polarity is qualitative, which means that there's no numbers involved. You simply either choose whether or not the molecule is polar or not polar. Now it's time to decide how to determine the molecular polarity, and as I mentioned above, let's take a look at the shape. What you're looking at for shape is a molecule that looks not symmetrical, or in other words, lopsided, or asymmetrical. Of the 5 shapes that we talked about, 2 of them will always yield asymmetrical or lopsided looking molecules. Those shapes are bent and trigonal pyramidal. You'll realize right away that these 2 molecular shapes both have a pair of electrons on the central atom. Bent have 2 pair of electrons, trigonal pyramidal have 1 pair of electrons. And these structures will always result in polar molecules. And the reason that these are always polar molecules is because when you zoom in on the picture, you will see that there's always one side of the nitrogen or the central atom that has a pair of electrons. And each one of these electrons is negatively charged. And so there's the negative side up here, and the other side, or the bottom side of this molecule, is the positive. I can talk about the same one on the bent. You can see that the top side always has electrons, in this case 4 electrons, and the bottom side has the elements. wherever there's a pair of electrons is always the negative side of the molecule. And we talked about polarity, how there's different sides. There's a positive side and a negative side. Well, in these polar molecules, there's the negative side where the electrons are and the positive side where the rest of the molecule is. And if you wanted to, you could draw a molecular dipole, which represents the overall polarity of the structure. And if you did that, not for the bonds, but for the overall molecule, you would draw a line pointing toward the more negative side of the structure and again crossing the tail. In this case, the positive side lies in between the two hydrogens because that is not falling on any bond, but the average of these two bonds is right in here in empty space. Now when it comes to the other one, the bond dipole is also pointing towards the arrows, pointing towards the electrons with the positive down below underneath the nitrogen. Now I'm not going to expect you to be able to label the dipole of a polar molecular molecule, but I'm just showing it to explain more fully what a polar molecule is. It is a molecule whose shape allows for lopsided or asymmetrical scenarios like these. Now I'm going to zoom back out and we're going to talk about the other three shapes, which typically are nonpolar. The other three shapes, linear, trigonoplanar, and tetrahedral, are falling under the side of the table labeled nonpolar. Here's an example of each one. You can see that on the central carbon of all three of these, there are no pairs of electrons. What that means is that the shape allows for the bonds to set up directly across from one another. And when they set up directly across from one another, they cancel each other out. When the molecule is symmetrical, meaning it's got the same elements on the outside and it's one of these three shapes, then it typically is nonpolar. Now the reason I say typically is because it's not always nonpolar. You can actually make a nonpolar shape into a polar molecule, and the only way to do that is to take the shape and replace one of its elements with something else. I'll explain to you using this example. Let's zoom in here and see if I can compare it with the CH4. Now I'm going to take CH4 and I'm going to compare it to CH3Cl. So if you look closely, you can see that I have a carbon in the middle, like I do up here. I have three hydrogens on the top, bottom, and left, but instead of a fourth hydrogen right, I replaced it with the chlorine. Now this shape remains tetrahedral because there are four bonds and no pairs of electrons. But because I replaced one of the outside elements with a chlorine instead of a hydrogen, now this molecule is labeled as polar. So there's a caveat to these nonpolar shapes. These three shapes are generally nonpolar only as long as everything on the outside remains identical. As soon as you change one of the elements on the outside from a hydrogen to a chlorine, as in this example, you will go from a nonpolar molecule to a polar molecule. And nonpolar molecules do not have a dipole. They don't have an arrow to show a positive side and a negative side because there are no sides to nonpolar. They are all equal in sides. But this other one does have a dipole, and since chlorine is more electronegative than the hydrogen, then we can label the dipole of this molecule to show the arrow going out towards the more electronegative chlorine with the positive lying closer to the carbon. But the point I'm trying to make is that you do not have a dipole for a nonpolar molecule, only for polar molecules. So in summary, you can pretty much stick to these shapes. If they are bent or trigonal pyramidal, they are polar, and if they're linear, trigonal, planar, tetrahedral, they're nonpolar. The only thing you got to check for is if it's a nonpolar shape, check to make sure it's actually nonpolar by making sure all the atoms on the outside are identical. If any one, 2, 3 change, it becomes a polar molecule. So here's the last slide, and it's a summary slide. Polarity can be described using the bonds or the molecule. First of all, bond polarity is quantitative and molecular polarity is qualitative. Qualitative means that it has a number value. Quantitative means it's either just polar or nonpolar. Bond polarity is dependent on differences in electronegativity. Molecular polarity is dependent on the molecular shape. And now hopefully you know the difference between a bond polarity and a molecular polarity. Thanks for listening.